Fine. Let's start. Number 10. Saturn's radio screams. Picture the most beautiful object in the solar system. The one on every poster, every textbook cover. The planet a child draws when you say the word space. Golden. Ringed. Serene. Now imagine you flew all the way out there, almost 1 billion miles, parked a spacecraft in orbit, and turned on your instruments to listen. And what came back wasn't silence, and it wasn't music. It was screaming. In 2004, NASA's Cassini spacecraft was closing in on Saturn after a 7-year journey. On board was an instrument called the Radio and Plasma Wave Science Experiment, run out of the University of Iowa by a physicist named Don Gurnett. And as Cassini approached, that instrument picked up something coming off the planet's poles. Not light. Radio. A flood of radio emission tied to Saturn's auroras, the same kind of shimmering light show we get here on Earth, except Saturn's version is broadcasting. Now, radio waves aren't sound. You can't hear them any more than you can hear the signal going to your car stereo. But the frequencies were close enough to our hearing range that the team could shift them down by a factor of 44 and drop them into something a human ear can process. And when they did that, when they finally listened to what Saturn was putting out, it didn't sound like a planet. It sounded like a choir of ghosts, rising and falling, warbling, voices that almost form words and then dissolve. Here's the thing. Astronomers had a plan for these signals. The radio emission is tied to Saturn's magnetic field, and the magnetic field is tied to the planet's rotation. So in theory, you listen to the rhythm of the screaming, and the screaming tells you how long a day is on Saturn. Simple. Except when Cassini measured it, the rhythm had drifted by several minutes compared to what Voyager had recorded back in 1980. The planet hadn't slowed down. A gas giant doesn't just casually change its rotation in 24 years, but its scream had. And to this day, nobody can fully explain why Saturn's radio clock refuses to keep honest time. So the most beautiful planet in the sky has a voice. We recorded it, and it's the sound of something that won't tell us the truth about itself. Number 9, the comet that sang. A comet is about as dead as an object can be. A lump of ice and dust and rock, maybe a couple of miles across, tumbling through the dark on a lonely orbit that only occasionally brings it anywhere near the sun. No atmosphere to speak of. No activity, most of the time. No reason on Earth to expect it to make a sound. So when the European Space Agency sent a spacecraft called Rosetta to chase down a comet with the almost unpronounceable name of 67P, Churyumov-Gerasimenko, nobody on the team was listening for a voice. They were listening for a magnetic field. Rosetta carried a magnetometer, part of a suite of plasma instruments, and as it closed in during 2014, that magnetometer started picking up oscillations. Regular ones. A rhythmic wobble in the magnetic environment around the comet, humming away at 40 to 50 millihertz. And here's what 40 millihertz means in human terms. It means far, far below anything your ear can hear. The lowest note a person can perceive sits around 20 hertz. This was almost 500 times lower than that. A pitch so deep it isn't a pitch at all to us. It's just a slow, silent shudder in space. So the scientists did the same trick. They took the signal and raised it by about 10,000 times until it climbed up into the range where a human being can actually hear it. And out came a sound that stopped the room. A weird, clicking, warbling song. Almost bird-like, almost electronic, coming off a dead rock in the middle of nowhere. The lead scientist, a man named Karl-Heinz Glassmeyer, said something you don't often hear a physicist admit out loud. He said, "This is completely new to us. We did not expect this, and we are still working to understand the physics of what is happening." That's the tell. That's the moment. They had spacecraft, instruments, decades of comet science, and a barren lump of ice was doing something none of their models predicted. The song didn't match the known plasma sounds of comets near the sun. It was its own thing. Later work traced it to an instability in the thin cloud of gas just starting to boil off the comet's surface. But in the moment of discovery, all they had was the recording. And the unsettling fact that the universe had, once again, decided to make noise when it had no business making any. Number 8. Jupiter's roar. Everything about Jupiter is too big. It's more than twice the mass of every other planet in the solar system combined. Its storm, the Great Red Spot, could swallow the Earth whole. And around it, invisible, is a magnetic field so enormous that if you could see it from here, it would appear larger in our sky than the full moon. That magnetic field is the planet's shield, and where it meets the solar wind, the constant stream of charged particles blasting off the sun, there's a boundary, a shockwave. The place where the solar wind, moving at over 1,000,000 miles an hour, hits Jupiter's magnetic wall and gets slammed to a stop. On June 24th, 2016, NASA's Juno spacecraft crossed that boundary. It was still days away from arriving at the planet, more than 5 million miles out. But that's how far Jupiter's influence reaches. And Juno had an instrument called WAVES, built at the University of Iowa, listening the whole time. When it hit the bow shock, the recording captures it perfectly. A long, tense buildup, and then a roar, a wall of noise as the spacecraft punches through the boundary and crosses over from the raw solar wind into Jupiter's own private magnetic empire. And then, years later, Juno gave us something even stranger. On June 7th, 2021, it made a close pass by Ganymede, Jupiter's largest moon and the largest moon in the entire solar system, bigger than the planet Mercury. And the WAVES instrument recorded the electromagnetic emissions coming off it. 50 seconds of sound shifted into our hearing range. And partway through the recording, there's a jump. A sudden, sharp change in pitch. The scientists think that jump is the exact instant Juno crossed from the night side of Ganymede into the day side. Let that sit for a second. You are listening to a spacecraft cross a shadow. You are hearing the moment it flew out of the dark and into the light of a distant sun around a moon nobody has visited in over 20 years. Space is supposed to be silent. And here's the largest planet we've got, wrapped in a roaring shield, with a moon that sings when the sunlight hits it. Number 7. The sun's roar. We've been circling the outer planets, out where it's cold and dark. Now, let's go the other way. Let's go toward the fire, because in 2021, humanity did something that for all of history had been simply impossible. We touched the sun, and we recorded what it sounds like from the inside. The Parker Solar Probe is one of the toughest machines ever built. It has a heat shield about 4.5 inches thick, designed to hold at room temperature on the side facing us, while the front edge cooks at thousands of degrees. Its whole job is to fly closer to the sun than anything ever has, again and again, diving in and whipping back out. And on April 28th, 2021, on its 8th close approach, it crossed a line that scientists call the Alph-Venn critical surface. That's the real edge of the sun. Not the bright surface you see, but the boundary where the sun's magnetic grip finally lets go, where the material stops being part of the sun and becomes the solar wind blowing out into space. Cross that line going inward, and you are, by every meaningful definition, inside the sun's atmosphere. Parker crossed it, and it stayed inside for about 5 hours. And the whole time, its Fields instrument was recording the electric and magnetic fluctuations around it, the plasma waves churning through the corona. Turn that data into sound, and you get the voice of a star, not a clean tone. A restless, hissing, keening churn. The noise of a place where the temperature runs to 1,000,000 degrees and the physics gets genuinely strange. And here's the detail that still gives me a small chill. That boundary, the Alfvén surface, the true edge of the sun, isn't a smooth sphere the way you'd draw it. Parker found it's wrinkled, spiky, full of ridges and valleys. The probe didn't cross it once. It dipped in and out, crossing back and forth over the edge of a star like a swimmer ducking under waves. We sent a machine into the atmosphere of the sun, and it came back with a recording. And the recording is proof that the thing we thought we understood best in the sky has an edge that nobody had ever drawn correctly. Number 6. The Vela pulsar's heartbeat. About 11,000 years ago, while humans on Earth were just beginning to plant the first crops, a star in the southern sky ran out of fuel and died. Not quietly. It collapsed and then detonated as a supernova, briefly outshining everything around it, and then it faded. But it left something behind. At the center of the wreckage, the star's core got crushed. Crushed so hard that the protons and electrons were mashed together into pure neutrons, packed to a density so extreme that a single teaspoon of the stuff would weigh billions of tons. What's left is a neutron star, and this particular one has a name. The Vela pulsar. Here's what a pulsar does. It spins, and it spins fast, and it fires beams of radiation out of its magnetic poles like a lighthouse. Every time one of those beams sweeps across the Earth, our instruments catch a pulse. Vela spins about 11 times every single second. 11 times. A city-sized ball of crushed dead star rotating 11 times a second, and it's been doing it reliably for 11,000 years. When you convert those pulses into sound, you get a heartbeat. A steady, mechanical, relentless thud, thud, thud. The pulse of a corpse. And it's almost perfect. Almost. Because every so often, the Vela pulsar does something that shouldn't be possible for a solid object. It glitches. Suddenly, without warning, it speeds up. The heartbeat jumps. For decades, astronomers couldn't figure out why a dead star would abruptly spin faster until they realized the answer. Inside a neutron star, beneath that solid crust, there's a superfluid. An ocean of neutrons with no friction at all, spinning at its own rate, and every now and then, that hidden interior lurches, dumps some of its spin into the crust, and the whole star twitches. A starquake. You are listening to the heartbeat of something that died before recorded history, and every so often, the thing shudders. No light, no warmth, no life. Just a beat, out in the dark, keeping time it doesn't know or care that anyone is counting. Number 5. The chirp of two black holes colliding. For 100 years, it was just math. Einstein wrote down his theory of gravity in 1915, and buried inside the equations was a prediction. If you took two truly massive objects and swung them around each other hard enough, they would shake the fabric of space-time itself. They'd send out ripples, gravitational waves, spreading outward at the speed of light, stretching and squeezing everything they passed through. Einstein predicted it, and then he spent years doubting it was real, and then he mostly gave up, because the effect was so unimaginably tiny that he was sure no one would ever detect it. He was almost right. It took until September 14th, 2015. On that morning, two enormous detectors in the United States, one in Washington State, one in Louisiana, machines called LIGO, felt something pass through them. A ripple. The stretch was smaller than the width of a proton, smaller than 1,000th of the width of a proton, across instruments miles long. But it was there, in both detectors, 7,000ths of a second apart, exactly as a wave moving at light speed should arrive. They traced it back. 1.3 billion years ago, in a distant part of the universe, two black holes had been locked in a death spiral. one about 36 times the mass of the Sun, the other about 29, circling each other, faster and faster, closer and closer, until they slammed together and became one. And when they merged, about 3 times the entire mass of the Sun vanished, converted instantly into pure gravitational energy, radiated out into the cosmos. For a fraction of a second, that collision released more power than every star in the observable universe shining at once. And when you take that signal and turn it into sound, it's almost insultingly small. A little rising whoop. A chirp, they call it. It sweeps up from about 35 hertz to 250 hertz in about a fifth of a second, and then it's gone. That's it. That's the sound of 2 black holes destroying each other. A noise shorter than a heartbeat that traveled for 1.3 billion years to reach a machine we built specifically to hear it. The head of the project, David Wrightsey, stood up and told the world, "We did it." And then he said the line that still lands. It's the first time the universe has spoken to us in gravitational waves. Number 4. The deepest sound in the universe. Somewhere out there, right now, a single note is playing. It has been playing continuously for about 2.5 billion years. It has never stopped, not once, not for a single day in all that time, and it will keep going long after you and I and everyone we've ever known is gone. It is the deepest sound in the known universe, and we have recorded it. The note is coming from the Perseus galaxy cluster, about 250 million light-years away. A galaxy cluster is one of the biggest structures the universe builds. Hundreds or thousands of galaxies bound together, and swimming between those galaxies is a vast ocean of hot gas. At the heart of Perseus sits a supermassive black hole. And in 2003, an astronomer named Andrew Fabian, working with data from NASA's Chandra X-ray Observatory, noticed something in that gas. Ripples. Faint, regular ripples spreading out through the cluster, like the rings you get when you drop a stone into a still pond. Except these rings were hundreds of thousands of light-years across. Ripples in a medium are pressure waves, and pressure waves are sound. So Fabian's team did the arithmetic and worked out the pitch, and the answer is almost too strange to say out loud. The note is a B-flat, an actual, recognizable musical note, but it is a B-flat, 57 octaves below middle C, 57 octaves. Your piano has about 7. This note is so deep, so impossibly low, that it sits more than 1,000,000 billion times below the lowest sound a human being could ever hear. To release the sonification in 2022, NASA had to raise the pitch by hundreds of quadrillions of times just to bring it into range. But strip away the trick, and here's the raw fact. A black hole is playing a single sustained chord into a cloud of gas the size of a galaxy cluster, and it has held that note for 2.5 billion years. That's longer than there has been complex life on Earth. When that note started sounding, the most advanced thing alive on this planet was pond scum, and it's still playing. The universe has a lowest note, and it belongs to a black hole, and it does not care that we finally learned to hear it. Number 3. A black hole caught eating a star. Most of the time, a black hole is invisible. It sits there, silent, and if nothing falls in, there's nothing to see. But every so often, a star wanders too close, and when it does, the universe hands us the most violent home movie imaginable. In 2014, a network of small telescopes called the All-Sky Automated Survey for Supernovae caught a flash of light at the center of a galaxy about 290 million light-years away. They named it after their survey, SSN 14Li, and what they had caught was a star being murdered. Here's how a black hole eats a star. It's not a clean swallow. As the star falls in, the near side gets pulled far harder than the far side, and the difference tears the star apart. Astronomers call it spaghettification, which sounds almost cute until you picture it. The star is stretched into a long, thin stream of glowing gas, and that stream whips around the black hole and forms a searing hot disk, spiraling inward, heating up to millions of degrees, screaming across the X-ray part of the spectrum as it goes over the edge and out of the universe forever. An ASASSIN 14 Li was close enough and bright enough that scientists could record the whole thing, not just in one kind of light, in X-rays with Chandra and Swift and XMM Newton, in ultraviolet, in visible light, in radio. They watched a star die from every angle at once, in real time, across the electromagnetic spectrum. It became one of the most studied acts of destruction in the history of astronomy. And then there's the twist, the detail that turns this from a tragedy into something almost grotesque. The black hole couldn't keep up. The star's shredded remains were pouring in faster than the black hole could consume them, and so some of that material got flung back out. A fast wind of debris blasted away from the black hole, detected in the radio data. The monster took a bite too big to swallow, and it choked, and it spat part of its meal back into space. We recorded a black hole eating a star from across 290 million light years of empty space, and we caught it gagging on the corpse. Number 2. The collision that forged gold. Look at your hands for a second. If you're wearing a gold ring or a gold chain, or you've got a filling in your teeth, I want you to understand where that gold actually came from. Because it did not come from the Earth. Not originally. The Earth is far too gentle a place to make it. Gold can only be forged in one of the most violent events the universe is capable of. And in 2017, for the first time in history, we recorded it happening. On August 17th, 2017, the LIGO detectors, along with a European detector called Virgo, felt another ripple in spacetime. But this one was different from the black hole chirp. It was longer, and it climbed higher. And the pattern told the scientists they weren't looking at black holes this time. They were looking at 2 neutron stars. 2 of those crushed dead stellar cores. Each one heavier than the sun, but only about the size of a city, spiraling into each other about 130 million light years away. And then, about 1.5 seconds after the gravitational waves arrived, space telescopes caught a burst of gamma rays from the exact same spot in the sky. That was the starting gun. Within hours, around 70 observatories all over the world swung to that patch of sky, and they found it. A new point of light in a galaxy called NGC 4993, glowing where nothing had been glowing before. A kilonova. And as they watched it over the following days, its color shifted from blue to red, and the spectrum told the story. The collision of those 2 neutron stars had blasted out a cloud of debris, moving it up to 1/5 of the speed of light. And inside that cloud, heavy elements were being born. Gold, platinum, forged in the wreckage, right in front of our instruments. And the amount is staggering. A single one of these collisions is estimated to produce many times the entire mass of the Earth in gold and platinum alone. So, here is the truth that recording gave us. Every piece of gold you have ever touched, every wedding ring, every coin, every gram of it was made in a catastrophe exactly like this one. 2 dead stars colliding, somewhere, billions of years ago, long before the sun existed. We finally caught the universe in the act of making the most precious thing we know. And it turns out the only way to make it is to destroy something first. Number 1. The sound of the Big Bang. We've listened to planets and comets. We've listened to a star's atmosphere and the heartbeat of a corpse. We've heard black holes collide and a note that's been ringing for billions of years and the exact moment gold was born. And now, for the last one, we're going all the way back Not millions of years. Not billions. All the way back to the beginning. Because it turns out, the universe made a sound at the very start, and we have reconstructed it. For the first few 100,000 years after the Big Bang, the universe was nothing like it is now. There were no stars, no galaxies, no planets. There wasn't even clear space to look through. The whole cosmos was a dense, blazing hot fog of plasma, so thick that light couldn't travel through it. And in that fog, pressure waves were rippling back and forth. Actual sound waves, moving through the primordial soup of the newborn universe. Then, after about 380,000 years, the fog cleared, and the light that was released is still arriving today, spread across the entire sky. We call it the cosmic microwave background, and frozen into it is the pattern of those ancient waves. In 2003, a physicist named John Kramer at the University of Washington got a question from a fifth grader working on a science project. The kid wanted to know what the Big Bang sounded like. And Kramer realized he could actually answer. He took the data, first from NASA's WMAP mission, then later, in a higher fidelity version, from the European Planck mission, and he converted those frozen pressure waves back into sound. He reconstructed the roar of the infant universe. Now, to hear it, he had to raise the frequencies by a factor of 10 to the 26th power. That's a 1 with 26 zeros after it. The real sound was so unfathomably deep that no ear, no instrument, nothing could ever have heard it directly. And when you play it, it's a low, swelling, descending roar. And there's a reason it descends. As the early universe expanded, it stretched its own sound waves, dragging them to lower and lower pitches. So the sound of the Big Bang isn't a bang at all. It's a falling tone, a deep, receding hum, sliding downward as the cosmos grew. And here is where I want to leave you. That light, the cosmic microwave background, is not somewhere far away. It is passing through you right now. It is coming from every direction in the sky at once, the faint afterglow of the moment everything began. And a tiny fraction of the static on an old, untuned television set is literally that ancient light. We are not looking back at the beginning of the universe from the outside. We are still sitting inside the echo of it. The sound has been falling, quietly, for 13.8 billion years, and it is falling still, all around us, whether or not there is anyone left to listen. We just happen to be the part of the universe that finally learned how to hear itself begin. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.